Welcome back. In this video, we're going to give a very brief introduction and overview of what we're going to be talking about in semantic analysis. Let's take a moment to review where we are in our discussion of compilers. So we talked about lexical analysis, and from the point of view of enforcing the language definition, the main job that lexical analysis performs is to detect input strings that have words in them or primitive symbols that aren't part of our language. The next step is parsing, and we finished talking about that too. And again, from the point of view of trying to determine whether a program is well formed or not, or whether it's a valid program, the job of parsing is to detect all the sentences in the language that are ill-formed or that don't have a parse tree. And finally, what we're going to be talking about now, what's going to occupy us for quite a while, is semantic analysis. And this is the last of what are called the front-end phases. So if you think of lexical analysis, parsing, and semantic analysis as being filters that progressively reject more and more input strings until finally you're left, after all three phases have run, with only valid programs to compile, well, semantic analysis is the last line of defense. It's the last one in that pipeline, and its job is to catch all potential remaining errors in a program. Now you might ask yourself, why do we even need a separate semantic analysis phase? And the answer to that is very simple. There are some features of programming languages, some kinds of mistakes you can make, that parsing simply can't catch. Parsing, using context-free grammars, is not expressive enough to describe everything that we're interested in a language definition. So some of these language constructs are not context-free. And the situation here is very, very similar to what it was when we switched from lexical analysis to parsing. Just like not everything could be done with a finite automaton, and we wanted to have something more powerful like context-free grammars to describe additional features of our programming languages, context-free grammars by themselves are also not enough, and there are some additional features beyond those that can't be easily expressed using context-free constructs. So what does semantic analysis actually do? In the case of coolC, it does checks of many different kinds, and that's pretty typical. So here's a list of 6 classes of checks that are done by coolC, and let's just run through them quickly. First, we want to check that all identifiers are declared, and we also have to check that any scope restrictions on those identifiers are observed. The coolC compiler has to do type checking, and this is actually a major function of the semantic analyzer in cool. There are a number of restrictions that come from the object-oriented nature of cool. We have to check that the inheritance relationships between classes make sense. We don't want classes to be redefined. We only want one class definition per class. Similarly, methods should only be defined once within a class. Cool has a number of reserved identifiers, and we have to be careful that those aren't misused. And this is pretty typical. Lots of languages have some reserved identifiers with special rules that have to be followed for those identifiers. And actually, this list is not even complete. There are a number of other restrictions, and we'll be talking about all of those in future videos. The main message here is that a semantic analyzer needs to do quite a few different kinds of checks. These checks will vary with the language. The kinds of checks that coolC does are pretty typical of statically type-checked object-oriented languages, but other families of languages will have different kinds of checks.